Hey everyone, Mr. King here, talking about models in science today. We've been doing a lot of experiments in class, and there is a lot of different uses for models and experiments, and that's the way we test out a lot of things to see how things work. And there's a lot of great things that models can do. You can see the title of this is Saving the World One Crash Test Dummy at a Time. So we definitely use crash test dummies a lot, and they help us out a lot. I'm going to show you a little video here that's going to show how we use a model of a human, which we call a crash test dummy, to figure out the effects of a car crash on a person. So check this out.
Today, no new car hits the showroom without being rammed into walls, barriers, and other automobiles to make sure you're safe in your vehicle. Initially, crash test sites focused on what happened inside the car. But drivers and passengers aren't the only victims of crashes. Pedestrians are often involved in serious accidents, and they don't come with airbags. But how do you make cars safer for people walking down the street? You do pedestrian crash testing. It's research so cutting edge that there are only a handful of testing facilities in the world. Here at Honda R&D Americas in Raymond, Ohio, these guys have been studying pedestrian collisions for 5 years. It's the major focus of their crash test site. The man in charge of the pedestrian crash test is Honda's automotive safety testing specialist, Brad Arn. Brad and his team work with a highly specialized dummy, designed just for Honda. They spent $1 million developing the prototype. Each Polar 2 costs $300,000, and only 3 exist in the world.
The Polar 2 dummy actually has a knee that has 4 ligaments in it, just like a human knee. It has a tibia that's kind of consumable, that's replaceable in between tests if it is to break. The ribs actually use a different type of sensor than a normal dummy. The arm has better range of motion. It's just more anthropomorphically correct than an actual dummy that you'd use in a frontal collision.
The Polar 2 may be the most evolved crash test dummy in history. And Brad and his team are getting ready to run theirs over with a big SUV. Today, their concern is preventing you from being killed by head injuries. They're focusing on where the bumper is placed and the shape of the hood.
So what's going to happen is the Acura MDX is going to start down about 90 meters down the tunnel. We'll hook it up to the cable and get the cable in the car going up to 40 kilometers an hour, and it'll hit this trigger on the floor, releasing the magnet.
1 meter from impact, the car will hit the trigger. Everything is calculated so the dummy will be standing still at the moment of impact.
The dummy does not have any time to actually come down or move. From the time the dummy is released to the impact is about 30 milliseconds. That's 30 thousandths of a second. It's that quick.
The exact position of the dummy at the time of impact is crucial.
The goal is to get him in the same position each time so our results are repeatable, so that we can make effective countermeasures based on repeatability.
Cameras are ready, sensoring's ready, lights are ready.
All right, give me a countdown.
So you can see, no human wants to really sign up for that job. That's not anything we're going to volunteer for. That would be very dangerous. Also notice the scientist in that experiment said we want to make sure we get the crash test dummy in the exact same spot so that we can repeat the experiment over and over. That's a controlled experiment like we've been talking about in class. You change one variable and see how that affects the results. So their variable that they would change, since the dummy is going to be in the exact same spot, they'd change the speed of the car or maybe the angle that it hit it. But you'd have to have the dummy in the same place each and every time. So model is a representation of an object or event used as a tool for understanding the natural world. That was a model of a human. So that helps us understand how humans can be effective by standing in front of a car, which is not a fun test for any real person to do, but by having a model of a human, we can tell where a human would hit on the hood of the car and how they can adjust the make of the car in order to make it a little bit friendlier for a human. So we got three basic types of models: physical models, computer models, and idea models. And any model that you make can be classified into one of these three categories. So we'll talk about each one a little bit more. So a physical model is a model that you can touch and see. It is anything that you can grab. So if there is a paper airplane, you can grab that. You can hold that in your hands. A crash test dummy, you could actually go up and you could throw that. A globe of the earth, you can put your hands on. So anything that you can see with your eyes but also touch. It has to be both. So you have to be able to actually reach out and grab it. It has to be a physical object that you can hold. That's called a physical model. Second type of model is a computer model, and these are getting more and more popular as our technology evolves and we get used to using computers for different things. Example of a computer model, the controlled lab we did in class last week, the coats in a closet. Okay, that computer model simulated putting coats in a closet for 5 minutes, and it showed us the results. It's a model because it is like the objects themselves, but it wasn't real. A weather map is another computer model. If you guys watch the news at all or ever see the forecasts, they show a picture of the United States and show the different fronts, and you can see the picture I have here where you can see some of the warm fronts and cold fronts coming in. That's a computer model. So anything that is on a computer screen is going to be a computer model. Now that's different from the physical model, because on the physical model, so it's two things. You can see it and touch it. A computer model, you would just be able to see. You can't really reach into your computer and touch it. So that's a little bit different from the physical model. Now the last type of model is called an idea model. And an idea model is someone's thoughts about something that can't be made into a physical model or a computer model. And as you can see on the screen here, it says these are the least common types of models. And the reason why these are not very common anymore is because we can make a computer model for almost anything. One example of an idea model is Einstein's theory of relativity. You guys know it as E equals mc squared. And it's talking about how objects travel according to their mass at the speed of light and how that's constant. You could do computer simulations to prove that now. But the thought process behind it, that's an idea model. That's something you could never say, here, look at my idea model of the theory of relativity, and hand someone something. That would not work out that way. So these are very, very uncommon at this stage in our development because, like I said, we can make a physical model of almost anything. You can make a model of a computer drawing now. They have models where you can send in information into a computer and you press the print button and it makes a 3D object. It actually makes the object what you have drawn on the screen, not just on a piece of paper, but out of different types of clays and plastics. It molds it into it. So it's pretty limitless what we can do at this point. What can models do? Okay, we use these. Models have several different uses. First thing is models communicate. They can communicate information for different tests that you want to do, different observations and ideas. For example, we are communicating when we're done with using a globe. You can communicate how people travel around the world. You can communicate the way that the sun revolves in different parts of the earth. All those things work to communicate findings. Models can also test predictions. We just saw the video where the crash test dummy, you predict that a car going 40 miles per hour hitting a person would maybe snap their neck or break their leg. You can test that out, and like we talked about earlier, I don't think there's a whole lot of volunteers who are saying, yeah, pick me. I'd love to jump in front of a moving car. That's just probably not a really wise decision. And then probably the most important one, models can save time, money, and lives. A Lives, obviously, with the crash test dummy. Anytime we want to know the effects of different chemicals and things like that, you can also test that out on different types of models to see. Time and money, that was big with our computer lab simulation where we did the coats in the closet. You guys, instead of having to sit for 5 minutes, you pushed a button and it simulated 5 minutes. We talked about the amount of money it would cost for me to run that lab for you guys. I would have to buy 45 jackets for each person or for each group. That's a huge amount of money. And so by having a computer model, that allows us to test out all those ideas without all the expense. Okay? Models can also be very, very simple. A paper airplane is a model that can test out a prediction. What would happen if the wings were longer? You just fold the paper a little differently. Rather than spend millions and millions of dollars on things, you can spend 10 cents on a piece of paper and then see how those results change. Now, there are some things that models cannot do. Models are not going to give you perfectly accurate results. The crash test dummy being hit by a car is a great example of how we use models, but it's not perfect. That's not a real person. So in order to know for sure 100% how a real person would be affected by a car, you'd actually have to have a real person be hit by a car. So models can give us a great idea of what would happen, but they're not going to be 100% perfect. And another great thing about models is that you can always change them. Okay? They change over time as new observations and discoveries are being made. So as we discover that there's new islands or there's new planets in our solar system, we change those models over time to make it easier to study, and that way people can understand the way our universe works or the way our world is formed and things like that. So models do all kinds of great things. They help us tons in science. They save us time, money, they communicate. All these things are really, really great things that they do, but when it comes down to it, they still have some limitations. There's still some things they can't do. They're not perfect. They're not an exact science to what you really want to test. Even with our coats in the closet experiment, a lot of you guys said one of the weakness was you don't know if that data is real. You don't know for sure. That's how warm a coat would get if you left it in a closet for 5 minutes. So even though they're great, there are some drawbacks to using them as well. All right, guys, that wraps it up for models. Head on over to QuizStar, take your quiz. We'll call this one Models in Science. Make sure WSQ is done. Make those good questions. We talk about making sure that your classmates have to think when they answer those questions. So make them good ones that aren't just one word or two word response. Make them ones that you'll have a good conversation. All right, I'll see you guys tomorrow.